I'm Tong. I'm a software engineer at the Azure Machine Learning team in Boston. So in this presentation, we demonstrate an interactive environment for deep learning workflows where we take the bring compute to data approach by attaching hardware accelerators to a Spark cluster to speed up computation-intensive workloads such as training a DNA model. Our ultimate goal is a single environment for workflows that requires both big data and big compute support. This is a challenging task because the workloads of these two types typically require different software and hardware supports, so that in practice they are handled differently on separate systems. A good example is deep learning from large data sets. In this particular case, the compute part is more challenging because we all know that training a DNA model is extremely computation intensive, so that it has to be hardware accelerated. The common approach is to use GPUs, but at the same time, companies has been developing their own hardware acceleration strategies. So as the first step, we focus on the support for deep learning workflows. As shown in this diagram, a machine learning workflow starts with data preparation. For large data sets, a Spark cluster should be efficient to handle the first phase. The second phase of model building and training is iterative. It involves many iterations of building the model, training it, evaluating it, and tuning the hyperparameters. Due to the iterative nature of this phase, it will be very productive for users to be able to perform their experimentations in an interactive repo environment such as Python notebook. However, the primary obstacle to deliver such an interactive experience is the long-running training jobs. So our primary design goal is to support high-performance training. So in the last phase, once the user has a satisfying model, she can deploy it for production. Our strategy for high-performance training is a hybrid architecture in cloud that is dynamically configurable. The system starts with a Spark cluster. Based on the computation need of an application, VMs with special hardware configuration can be added to the Spark cluster. For hardware acceleration. So the execution model is pretty simple, and the entire deep learning workflow will be executed on the Spark cluster, but with computation-intensive jobs such as training a DNA model being offloaded to the attached VMs for high performance execution. So the message passing interface framework is used to support distributed training across those attached VMs. Once the computation is finished, those attached VMs can be either stopped or removed to save cost. So this is a very cost-effective solution. Besides high performance, another design goal is ease of use. Users should be able to easily deploy, reconfigure, program, and debug this system Right now, CNDK is used as the deep learning framework. Users should be able to choose other deep learning framework as well. The implementation of this strategy on Microsoft Azure Cloud Platform is open sourced through MMLSpark. MMLSpark stands for Microsoft Machine Learning for Apache Spark. It is an open source library providing a suite of tools, algorithms, and expansions of Spark to enable various new machine learning and HPC workflows. Besides deep learning on CNDK, it integrates the OpenCV image processing library and the LightGBM gradient boosting library into the Spark ML ecosystem, all written in high-performance native code. Recently, MMLSpark also released a new runtime that enables Spark pipelines on unstructured streaming to be used as a low latency and distributed web services. Part of the image processing work has been contributed back to the Spark. So before diving into the implementation details, I would like to highlight the key benefits you can get from this system. I will use examples from my own experience using it. Firstly, high-performance training enables an interactive environment where a user can experiment quickly. I didn't have any hands-on experience on deep learning before this project, so I learned it by playing examples in this interactive environment. I still remember the first time I tried the example from CNDK on my powerful portable workstation here. I launched the job in the morning, and it didn't finish before I had to go home. So now you can play this kind of examples interactively in this environment. The training time has been reduced from hours, many hours, to minutes. So an interactive environment leads to productivity. To evaluate this implementation, I want a large data set and a large model. And ideally, I hope the training algorithm can converge fully so that I can prove our implementation is correct. It takes us within a week from deciding to use the NIH chess X-ray dataset to achieving an accurate model which contains 46 million parameters. The best part is we can train the final model using less than $10. And the training takes less than an hour. The rest of the workflow takes less than an hour on the Spark cluster. So if you want to save extra $2, you can actually attach the GPUs while the Spark cluster is processing the data. This is the architecture for our initial implementation on Microsoft Azure Cloud Platform. The system starts with a Spark cluster configured with relatively cheap machines for data processing. Given the computation need of an application, VMs with hardware accelerators such as GPUs can be attached to the system through Azure Virtual Network for hardware acceleration. For a typical data science workflow, data preparing, featureization, and later model evaluation can be performed on the Spark cluster, while the expensive training job is offloaded to the attached VMs for high-speed execution. So IMPI is used to coordinate the distributed training across multiple attached VMs. If tightly coupled parallelism is employed by an application, high-speed networking technologies can be added, such as InfiniBand and RDMA. RDMA stands for Remote Direct Memory Access. Those configurations can be added to those attached VMs to support high-efficiency data exchange. MMLSpark is installed on the nodes of the Spark cluster to tightly integrate these two systems. Data exchange is through local files for small datasets and through direct access to the HDFS system on the Spark cluster for large ones. To enable launching the jobs on the attached VMs and direct access to the HDFS system, the virtual network need to be configured to allow SSH and RDMA protocols. As I mentioned earlier, once the application is finished, the attached VMs can be either stopped or removed to save cost. Users interact with this computing system through a browser-based Jupyter Notebook client, which is hosted on the Spark cluster. User can manage the computing resource in this system either through Azure Portal or through scripts provided by MMLSpark. User can also track the output of an application in real time through Young Web UI as if this application were run locally. So now let's take a look at how we use this system. The initial setup is easy. We provide one-click deployment experience. You can go to our GitHub page, click on the link as shown in the screenshot on the right. It will open the parameterized configuration file generated by our build system in Azure Portal. Azure Portal will then prompt user to enter the required parameters in the form as shown on the right. So the parameters are self-explained by their names, so I will not go through them one by one. The initial setup consists of a Spark cluster and one GPU VM. User can configure the size of this system by specifying the corresponding parameters in the form. If more computing resources are needed by a particular training task, more GPUs can be added to the system. And in Azure, a VM can have up to 4 GPUs on it. Attaching a new VM is as simple as the previous one. You just fill the parameters in the form. For each new VM attached, user is required to log into the Spark cluster to run this script to set up the passwordless connection between the Spark cluster and the attached VM. The reason is simple because MMLSpark do not remember user credentials, so user have to type their credentials twice. The table lists a sample of options for GPUs. For our test system, we choose the cheapest one, which is Tesla K80. If we upgrade it to Tesla V100, we should expect a 2x speed up in performance, but it will also cost more. Now we have the system physically set up in Azure. The question is how we program it. MMLSpark provides the same machine learning pipeline API as in Spark ML with estimators and transformers. In this example, CNTK learner is an estimator representing a model to be trained on 2 VMs. Each one has 1 GPU. The fit method of the estimator returns a transformer, which represents the trained model, which can be used for later evaluation, for example, to score the test set. We also compare the performance difference between CPU and GPU here. In this case, we train a convolution neural network using 1/6 of the CIFAR-10 dataset. We time the 2 runs with or without GPU for 30 epochs on the same VM. As you can see, using GPU in training can have a 40 times speed up. The evaluation result on the test set is shown in this confusion matrix. To test over implementation, we want a much bigger data set and a much bigger model. The NIH chest X-ray dataset is one of the largest chest X-ray datasets publicly available today. If we load the entire dataset into memory, the size will be in the order of terabytes. We choose an AlexNet with 64 million parameters to train a binary model with this dataset. We use half the dataset for training and reserve the other half for evaluation purpose. Each image is downsized to control the model size. Given a training task at this scale, we want to use multiple GPUs. CNTK has this data parallel 1-bit SGD algorithms, so we use it for parallelization. Using 4 GPUs across 2 VMs, the training algorithms fully converge at the 55th epochs. The training time is under 1 hour. At the same time, we also achieve a relatively large mini batch size of 112. And the full converge is also validated by the evaluation result as shown in the confusion matrix here. To detect networking overhead, we also run the same training problem with 4 GPUs, but across 4 VMs. As you can see, no performance difference is observed. So we have shown an interactive environment for fast experimentation with deep learning workflows. So what's next? Firstly, this architecture can be easily extended to support other workflows that requires big data and big compute supports. We just use the same strategy where we use Spark cluster for big data processing, and we attach VMs with hardware acceleration to support large-scale computation efficiently. Because expensive special hardware resources are consumed only when needed, so this is a very cost-effective solution. The diagram shown on the right envisions some of the future work. For deep learning workflows, we will use ONNX to represent a DNN model. ONNX stands for Open Neural Network Exchange format. The advantage of using a common format to represent DN models is that we can exchange those models freely between the subsystems and also between different deep learning frameworks. In this way, other deep learning frameworks can be easily added to the system. The attached VMs can also be heterogeneous. For example, we can use GPU VMs for training, and we can use FPGA VMs for high-performance evaluation, where FPGA is configured at runtime to reflect the architecture of a specific deep neural network. To conclude this presentation, I would like to call out, this is a very cost-effective solution with a significantly performance and productivity boost. Hopefully, this system can enable much faster research and development progress for our users. And thank you, and please give MMLSpark a try.
Thank you, Tong. We have time for questions if anyone has questions. Otherwise, you can get in line for lunch.
There should be at least one. Nobody asked about Project Hydrogen. Project Hydrogen. Yeah, so. No, so the two projects have the same goal. Yeah. So, yeah.
So can I ask a question? Like, if I just get started with this one, what's the hardware requirement? Does this is an optimized way to get started?
There are no specific hardware requirement. So basically, it's a cloud-based solution.
Right.
So any VMs that are available on a particular cloud platform, we support that.
Okay.
But for deep learning, different workflows or workloads require different hardware support. So the general guideline is, depends on a particular workload, you pick the right VM with the right hardware configuration and to achieve high performance.
Gotcha. Thank you.
Quick question. All these MMLP Spark jobs are as Yarn jobs, it can be submitted, or?
I'm sorry.
All these workflows can be submitted as Yarn jobs? Yarn.
So,
Are you getting me?
Yang is the resource manager we use, but there are other resource managers and available. There are Mesos and the Spark building ones. So,
Okay.
did I answer your question?
Yeah. So when we attach VMs, is it for GPU boxes, it can be treated as a normal Hadoop file system and it can read directly? Or?
Sorry, I cannot hear you clearly. I see. So, yeah. So I see. I understand your question. Those attached VMs is outside Yarn. That's what I think. That's.
So that means Yarn, Hadoop client will be installed on those GPU boxes as well to understand the Hadoop terminologies. Mm-hmm. Okay. Yeah, thank you.
Yeah. So, yeah, I think I forgot to mention that data exchange between the two worlds is through either local files for small data sets or through direct access to the HDF system for large ones. So we extended CNDK with HDF reader, which can deserialize data frames, track pointed into the HDF system in Parquet format.